Let's take a look at the central physics case measurement of specific characteristics of our world on the subatomic level. If you remember, we spoke previously about the very big difference between the magnitude of gravity and other forces. So there are different hypotheses that try to explain this phenomenon. For example, large extra dimension models, graviton, or micro black holes. And one of the hypotheses says that there are extra dimensions that exist in our world that we don't notice because they are very tiny. Look at the illustration on the left. So there is a lady walking on a wire, and for her, since she is a large entity compared to the wire diameter, it's essentially a one-dimensional object. But for a flea that sits on this wire, there is actually additional dimension, and she can consider the wire as a two-dimensional object. You can follow the link and see a nice cartoon by Daniel Whiteson about explanation what are those extra dimensions. And the way how you can prove the theory works or not is to make an experiment. In case of Large Hadron Collider, you design an experiment or look for a specific decay or a specific event, kind of event, that you can measure. And in some cases, events might happen with higher probability than in other cases. And some theories might explain those differences in probabilities. We will talk about this in more details at the third lecture. But for the moment, let's consider we need to measure a specific quantity related to events happening at Large Hadron Collider. And the measuring is a key for theory discrimination. Actually, there are plenty of theories has been studied already, has been tested already at Collider, and on this slide you see examples of various models that people has probed on ATLAS experiment, those are called ATLAS exotic searches, and it shows how well or how bad the limit or estimation of the model compares to the standard model. And you see that all the measurements are pretty much aligned with a standard model predictions. So let's look at the example of Higgs boson discovery. And in this case, it is a decay of Higgs boson into two photons. So you see how the theoretical picture of those events look like. So it is displayed on the top right part of the slide. It is so-called Feynman diagram that shows the process in theory. At the same time, there is a diagram or a histogram that shows the dependency of the number of events with respect to the mass of the event. And you see that there is a special bump that is highlighted in the middle of the histogram that shows the excess of the experimental data that has been measured at the experiment ATLAS with respect to the data that we expected to see under assumption that there is no such thing as decay of Higgs boson into gamma quants. Let's make a short detour into the Feynman diagram because it is a really powerful instrument for displaying the processes that happen on subatomic level. So at this particular diagram, you see a muon that transforms into something else. So at the same time, at this diagram, you see a time scale and a coordinate depicted by letter S. We start with a muon that and the time goes on the horizontal axis, and then it turns into something else like a muon neutrino and doubly boson, and then in turn this doubly boson turns into an electron, and anti-electron neutrino. Let's look at the steps. So those Feynman diagram consist of lines that are represented by that represent particles, and by dots that represent interaction points. Those are points in the diagram at which momentum, charge, and energy conservation must be valid. At the second vertex, we see creation of particles out of W boson, and this creation of particle also conserves also conserves mass and charge and energy of particles. So, in short, Feynman diagram represent a quantum process that unfolds in space and time, and consists of two basic elements, which are straight lines of particles and forces that are represented by wavy lines. Vertices represent interaction points which conserve energy and momentum. And those diagrams allow for calculation of probability of the processes that happens according to those. And in the following slides, we'll try to examine the appearance of so-called Z boson. It mediates a weak interaction along with W boson. And this kind of boson, Z boson, can decay into various modes or channels, as they're called by physicists, which are lepton-antilepton pair, neutrino-antineutrino pair, or quark-antiquark pair. Roughly, the ratio of those modes are presented on the slide, but more exact values of those ratios is specified at so-called particle data group database that contains information about all possible decays that has been recorded so far by all particle experiments. So discovery of Z boson has happened in 1983 at CERN, and it is very important part of standard model jigsaw puzzle. So let's take a look at the process that creates this kind of boson. So here is a more complicated Feynman diagram on the top left of the slide. So we start from the protons that collide with each other, and you see that every proton, it consists of 3 quarks. So it is up, and down quarks, and out of those 3 quarks, one becomes engaged with the other quark coming from other proton. So it is schematically represented at the center of the slide. So those 2 down quarks interact with each other and turn either into a gamma quant or a Z boson, which eventually decays into a muon and anti-muon pair. So another representation of the process, a more simplistic one, you can see on the top right of the screen. So just basically a Z boson decaying into muon-anti-muon pair. And since we have a particle that decays into a muon-anti-muon pair, such processes is called resonance, and its probability can be estimated from the diagram according to the formula that is depicted here. You can find more details by the link, but the most important part is the probability of the decay of this kind, Z boson decaying into muon-anti-muon pair, is the highest at the so-called invariant mass of 2 muons equal to mass of the Z boson that has been used to create those. So displaying this probability distribution on a mass, or according to mass axis, we see something like the Gaussian that is displayed on the right part of this picture. And the alternative mode of those 2 muons appearing out of the 2 down quarks interaction is through gamma quant. And since gamma quant doesn't have any specific mass, there is no specific peak at any specific region of the mass scale. So the distribution or probability distribution of finding two muons coming from a gametes is depicted on the histogram on the slide. And you see the shape of this histogram is quite different from the one we saw before. So in reality, we see a mixture of two processes together. So we see something that is a combination of a Gaussian-like shape and exponential-like shape. And somehow we can extract information about the Gaussian from the mixture of the model. And the most interesting part, the most interesting parameter that we can extract is actually mass of the Z boson. And we can do so, for example, by fitting a Gaussian and some exponential shape into the histogram that we got from the experiment. So here you see the d-muon mass spectrum. It is a histogram that shows number of events that have specific mass, and the range of the mass scales from very small value to very high, like 1,000 of GeV. And you see there are several peaks that sits on the shape of the background. Every peak corresponds to a specific particle that has been discovered at a certain point of time, and we will focus on the home task at finding parameters or finding mass of Z boson.